Welcome to the tutorial on simple linear regression in SAS. Simple linear regression is linear regression with a scale level outcome and one scale exposure variable. We're going to be using a data set called training, so you can find that in the tutorials folder within the class folder. Copy it into your ClassStat folder by right-clicking, go copy to, and find your ClassStat folder. The next thing is to run a libname statement, so go ahead and do that. The training data set has two variables. The first is the exposure variable called training, which is the average hours per week a student trained during the semester. The outcome variable is injuries, which is the number of injuries the student experienced during the semester. And so the research question is, among student athletes, does the amount of training time predict number of injuries? The first thing we want to do is inspect the data and run descriptive statistics. So go ahead and double click on the data set and just take a look here. And then the next thing we want to do is to run descriptive statistics. Since we have two scale variables, we can either use proc means or proc univariate. The next thing we can do is use the drop-down menus to create a scatter plot. So go under Tasks and Utilities, Graph, and go to Scatter Plot. Now make sure you can choose the right data set here. So click on the little data set and find training. For your X variable, that's going to be your exposure variable, so that's training. Your Y variable will be injuries. And the other thing we want to do here is go to Appearance, and we want to fit a scatter plot with a regression line. So we just make a little check mark there, and then we click Run. And as you can see here, we have a scatter plot with a regression line. It's going in the negative direction, so it looks like as training hours increase, the number of injuries decrease. So we can close out of our scatter plot. We don't need to save it. We'll move on to step 3, which is to state the null and alternative hypotheses and set the significance level alpha. For a simple linear regression, our null hypothesis is that there is no association between the exposure and outcome. The alternative hypothesis is that there is a significant negative association between training hours and number of injuries. And I say negative because that's the direction of the association I saw on the scatter plot. We'll set our significance level, our alpha value, at 0.05. Now we can actually conduct our linear regression analysis in SAS. The code looks like this. Our outcome goes on the left side, our exposure goes on the right side. We're going to request the Durbin-Watson statistic, DW, and confidence intervals. If our model is significant, we can move on to check assumptions 3 through 6 of linear regression. The way that we tell if our model is significant is by going to the analysis of variance table. And we look at this p-value. If this p-value is significant, the overall model is significant. Now we can check assumption number 3, no significant outliers. And the way we do that is by scrolling down and looking at this plot here of Cook's D. Cook's D will have a threshold, which is 4 divided by the number of observations in the data set. And you can see the threshold line here. And if there are any observations above that threshold, that means that observation is an outlier. Even though we do have an outlier here, we will move on as if we didn't. Our fourth assumption is that the residuals, the error terms, are independent. So the way we check that is by looking at our Durbin-Watson table. So we scroll up, find our Durbin-Watson table, and if the Durbin-Watson statistic is between 1 and 3, we can say that the assumption of independence of residuals is met. Our next assumption is homoscedasticity, or equal variances of residuals. The way we check that is by looking at the very first scatter plot here. And if we don't see any kind of pattern, particularly a funnel shape, if the data points seem relatively spread out, we can say that this assumption is met. Assumption number 6 is normal distribution of residuals. We can check this one with this specific plot, and what we don't want to see is all of the data points lined up on one side of the line or other. And we see here that is not the case, so we can say that the assumption is met. Now that we know the assumptions are met, we can interpret the results. The first statistic we'd like to interpret is called R squared, and we're actually going to look at the adjusted R squared. You can find that statistic right here in this table. R squared is a proportion, so multiply it by 100 to get a percentage. And what the R squared statistic tells us is about how much variation in the outcome can be explained by the predictor. So in this case, 18% of the variation in the outcome number of injuries is explained by the exposure training hours. Next, we'll go to this parameter estimates table. The first thing we see is the intercept, which is significant. That doesn't really concern us at this point. We'll get back to the intercept. The next thing we see is our predictor variable here. Let's look at the p-value. It is significant. So then let's look at the slope, the beta coefficient. This beta coefficient tells us the strength and direction of the association between the predictor and the outcome. And this association can be interpreted as a 1 unit increase in the predictor x is associated with a beta coefficient change, increase or decrease, in the outcome y. So now we can just plug in our variables and values from the parameter estimate table into this generic sentence, and we come up with a 1 hour increase in average training hours per week is associated with a 0.13, and I'm just rounding here, a 0.13 decrease, and we say decrease because this is negative. If it's below 0, that is if it's a negative number, the change will be a decrease. If it's above 0, it will be an increase. But in this case, a 0.13 in decrease in number of injuries. If we wanted to present this data in a presentation or in a paper, we would make a table that looks like this. Now, because the beta coefficient for our predictor variable was significant, that means we can use the regression equation to make predictions. We can predict values of y for any value of x that we plug in. First, we can plug in our significant numbers into this regression equation. So y hat is the predicted outcome, predicted number of injuries, equals the intercept. Here's the intercept. It is significant, so we'll include it here, plus the slope here, multiplied by average training hours per week. So we can substitute any theoretical number for average training hours per week here. So for example, let's plug in some different values of the predictor to find the predicted outcomes. If our predictor is 2 hours per week, 2 training hours per week, we can just plug that right into the regression equation, make the calculation, and it looks like training for 2 hours per week predicts about 7 injuries throughout the semester, so not a lot of training. If an athlete trained for 20 hours per week, they would have a predicted 4 injuries throughout the semester. If an athlete spent absolutely all of their time training 40 hours per week, they would have about 2 injuries per semester. Remember, all of the predictions are on average, so it's the average for all the people in the data set. So on average, if someone trains 20 hours per week, they would have 4 injuries. So that's all for this tutorial, simple linear regression in SAS.